Hello and welcome. It's Johannes again here with Packet Tuesday, and I hope you were waiting for today's episode because it really continues what we did in the last episode. In the last episode, we talked about router discovery and router advertisement. Well, today's episode will be all about neighbor discovery. Actually, the same RFC 4861. It covers both router advertisements and neighbor discovery. So what's the problem Neighbor Discovery tries to solve? Neighbor Discovery is IPv6's version of ARP. Now, why do we need to replace ARP? ARP itself actually allowed for various address sizes, various protocols. So ARP could theoretically be adapted for IPv6. There's one fatal flaw in ARP that makes it difficult to work with IPv6, and that's the fact that ARP requires broadcasts. And if you have large flat networks with like thousands of hosts in sort of one broadcast domain, well, in IPv4, ARP tends to take over, and you no longer have any bandwidth left for any normal traffic. So that's why IPv6 got rid of broadcast because it wants to support these large flat networks. Think sort of some IoT use cases or things like mobile carriers with thousands and maybe millions of devices, even sort of connected to one broadcast domain. That's sort of at least the vision kind of behind some of these design decisions. And that's why we need neighbor discovery. So neighbor discovery does the MAC address lookup with, or the link layer address lookup, I should say. It's not just for MAC addresses or Ethernet, but it does the link layer lookup without needing a broadcast. And that's the real trick here. And we'll dive into this a little bit later. But before we get here fully started, let's take a quick look at the RFC. So here we have our RFC, like I said, 4861. That's the RFC for neighbor discovery. You see there are a couple of sort of later updates, based of additions and such to these protocols. And we talked about some of this a little bit with a router advertisement in the last episode. When you're looking here at the index, you see routers advertisements, router solicitation, and then we have neighbor advertisements, neighbor solicitations. That's what we want to talk about today. So let's take a look at the message format while we are here in the RFC, before we sort of dive in further. So we have our classic ICMP v6 header. The messages, again, are typically your link local addresses that you have here for the IP address. And then the hop limit here in the IP header is again 255, similar to what we had with router advertisement, router discovery, to prevent these packets from entering from outside the network. As far as ICMP goes, we do have type 135. The code is again set for 0. And then we have our ICMP checksum. And then we have here 4 reserved bytes. Let me scroll up a little bit so you kind of see this here. And that's a little bit, again, another sort of design pattern that you find in IPv6, that you always have boundaries on 8-byte boundaries. So the first 8 bytes here, that's essentially your ICMP header. And that's why that target address that follows, we don't start it right after checksum, but we have sort of these 4 extra bytes here just to end up with 8-byte boundaries. The target address is then the IP address that we are looking for. And then we may have options. The one option that you typically have is the source link layer address, where basically the source of that neighbor discovery packet is giving you their link address, so you don't have like these catch-22 issues where, hey, in order to send you the packet back, I need to have your address, your MAC address as well. So that's why it's being added here. But anyway, let's dive in and look at the actual packet here. So let me pull this up. Uh, Today actually we'll just use TCP dump because these packets are simple enough. No real need to break out Wireshark. And let's go here for the first packet here. This is our neighbor solicitation packet. So that's the packet we just saw. Now let's play the usual game here and figure out what's what here in the header. So I do have my IP version 6. I do have my traffic class, and again remember it's sort of these 2 digits in the middle here. So that's 00. Then I have my flow label that goes sort of from here to here. So again, that's also all 0. Then my payload length, 32 bytes. 20, that's 32. Then I have my next header. This is the 3 alpha or 58, which means the next header is IPv6. Then I do have the hop limit FF or 255. And then we have the addresses. So here the source address, and then here the destination address. And I'll talk more about this later. I first want to take the pack a little bit apart. But our source address here is, of course, an FE8 address, a link local address. Our destination address is an FF address, which is a multicast address. FF02 means this is a link local multicast address. So a multicast address that will not be routed. The rest of the address we'll talk about later, because that's actually sort of a little bit the interesting part here. Then we have our ICMP header, so 8700, and let me switch to the ICMP header here. So 87, and that's 135, 128 plus 7. And then we have 00, our checksum, 7 echo, delta 2. And then we have these 4 0 bytes, this padding. So this is this reserved field here. And then we have the target address. So that's the address we are looking for. And then we have an option. The option type is 1. The option length is 1. Remember, IPv6, everything in 8-byte units. These 8 bytes here are our option. And then the option value is our MAC address. Notice here, 3 Charlie, 22, Foxtrot Bravo, Delta Alpha, Bravo Delta, Foxtrot 9. This is the MAC address here that we are communicating as part of the payload. And the reason this is sort of duplicated here is there could be bridges involved or such that may change the source MAC address here. So that's why we have it again here as part of the payload. But like I said, pretty straightforward, nothing really sort of, overly exciting yet. But I told you the interesting part here in some ways is the destination address. Let me write it out here, the destination address. So that's FF02 : 1 : FF 87 : 46 F2. So this is the address where this packet is going to. Let's take a look at what address we are looking for. We are looking for this address here, FE80 and then 46F2. Notice how this is the last 3 digits of that multicast address match the last 3 digits of the address we are looking for. If you're playing IPv6, Once you start accepting an IPv6, using an IPv6 address, you will automatically also listen to a multicast group where the prefix is FFO2:1:FF, and the last 3 bytes are the last 3 bytes of your IP address. So this avoids the broadcast part, because now I no longer need to broadcast the ARP or Neighbor Discovery packet. Instead, I can send it to this very specific multicast address, and it's referred to as a solicited multicast address. So 8746 Foxtrot 2. How do I come up now with a MAC address for this particular packet? Because I still need my Ethernet header. Well, so here we have the Ethernet header. We have a source MAC, we have a destination MAC, we have an Ethernet type. Well, look at the destination MAC. It starts with 3333. This prefix is set aside for multicast. So in IPv6, MAC addresses starting with 3333 are multicast. And then the last 4 bytes of that MAC address are the last 4 bytes of the multicast group that we would like to send a packet to. And that's here FF8746 Foxtrot 2. Okay, so this is the trick here. Just repeat that, because that's sort of one of the important parts here. If I want to do a neighbor discovery lookup, I take the last 3 bytes of the address I'm looking for, and then I send a packet to FF02:1 FF, and these last 3 bytes. So that's here our 8746F2. So this gives me the destination IP for our IPv6 header. And then I need the MAC address. For the MAC address, I just use 3333 and the last 4 bytes here of the destination IP address, and that gives me the MAC address. So now I can create my Ethernet header, I can create my IP header with the destination IP, and I can now send my packet. Actually, while I have the command shell up here, let me just show you these addresses. So EN7 should have some IP addresses here. So this is the configuration for my interface EN7. And as we talked about yesterday, last week, with the router advertisements, you will see there are multiple IP addresses, IPv6 addresses that I'm listening on. Let's just remember this CAF one. Let's look for this CAF address. Let me actually just copy that so I don't forget it. And now let's see what multicast groups this particular host is listening on. So yeah, and you see I'm listening here on FFO2:1 FF, and then 1F CAF, and this is the MAC address for it. 3333 FF 1F CAF. Just oops, I guess I didn't paste it correctly or copy it correctly, but anyway, that's his multicast address, and I'm listening for that multicast or for that multicast group. I'm registering for it since I'm using the specific IPv6 address. There's of course a chance that on our network there are multiple hosts that have addresses with the same last 3 bytes. The last 3 bytes don't have to be unique on the local network. That's okay. Then you have that packet go to multiple hosts in the network. If your switch does not understand multicast, it's likely going to send it to all of the host network. Then you don't gain the performance gain that you get by only using multicast, but it still works. It just works just as ARP worked before. And for most smaller networks, ARP is fine, and broadcasting these multicast packets on the switch is not really going to cause any issues. But better switches then will be able to listen for these multicast discovery packets that are being used, and then we can optimize the packet flow. And maybe we can talk about these MLD, multicast listener discovery packets and such in a future episode. But anyway, so this was our request. Now let's look. Let me just go up here. And let's look at the second packet here. And let me pull up the header diagram again for this second packet. So we can overlay this and again do our little walkthrough. So by now you should know that version 6, traffic class 00, flow label all 0, payload length 0020, so again 32. Next header, again 3 alpha or 58 for ICMPv6. Our magic hop limit of FF or 255. And then we have our source address and our destination address. These are now unicast addresses, of course, the respective link local addresses. So no more multicast here. The response is just unicast. And then let me switch here to the ICMP part. So now our type and code 88 and 00. So 88, 128 plus 8 is 136. So it's just one up from the 135 for the discovery message that we had earlier. Then we have our checksum 5884. Now, as far as the reserved part here goes, the first 4 bits here, actually the first 3 bits have a meaning. So that's here 6, and then we have our 0000. In the advertisement message, the first nibble here is the first 3 bits are really used as part of flags. And I have them down here. The 8 flag is reserved, the 4 flag is solicited, this 2 flag is override. So these 2 bits are set. The 4 and the 2 bit. The solicited bit is set whenever we are responding to a solicitation. There are things like gratuitous neighbor discovery, basic gratuitous ARP equivalents that where I'm sending a neighbor advertisement without you actually asking for it, then that solicited flag would be cleared. The first flag, the R flag, is the router flag. If this comes from a router, that flag would be set. And the override flag is sort of kind of interesting because it tells the host receiving an advertisement to update its MAC address cache. So that way, you basically overwrite any old information that is cached here. So this is our basic ICMP header, and then we do have the target address. That's the address we are actually resolving here. So here in our case, that matches the source address here, 46F2, 46F2. And then we have again an option. Option 2 here, again, length 1, meaning 8 bytes. And this is now the MAC address. So this is the actual answer here in terms of that this is the MAC address that I was asking for the particular host that's listed here as part of the target part of the address. So anyway, now, this is kind of how Neighbor Discovery works in IPv6. And I got two more packets here. I just want to show you quickly. Let me clean the screen here. So, and actually, let me just make these shorter. Without the X. So and let me do also without the E. Yeah, that's nice and pretty. So these were the first two packets we looked at the neighbor solicitation to the multicast address, and then the response being unicast. You may also see neighbor solicitation being done unicast. So this goes directly to the right IP address. This only works if I already have the MAC address. And you may say, why do I need a neighbor solicitation if I already have the MAC address? Well, this is kind of used to check reachability, if the host is still reachable and the MAC are still okay. So this is really just sort of to verify my cache, so I don't have to go through the neighbor solicitation again, going to the multicast address. Again, getting you a little bit less overhead here. If you think about it, in most networks, MAC addresses don't change all the time, particular with IPv6, where we do have addresses being not reused as we sometimes have in IPv4. So this is why we have this shortcut here, where we just check, well, you're still there, is it still your MAC address, and then you get the response back here. So anyway, like I said, it's actually relatively straightforward as a protocol, very similar to ARP in scope. We also have sort of duplicate address discovery, where, like I said, the equivalent is sort of gratuitous ARP. That's all the same. That all still exists here with neighbor discovery. Nothing really changed from a security point of view. Now, remember, theoretically, these ICMP packets, they could be routed. Unlike ARP, for ARP, there's no way to get to route it. But by setting that hop limit to 255, we basically put an end to having these packets routed, and then someone doing like neighbor discovery spoofing from outside the network. But inside our network, neighbor discovery spoofing is still possible. It's still a thing. There are tools for it, just like there are for ARP spoofing. There is actually a protocol called SEND, Secure Neighbor Discovery. Nobody really uses it. It's fairly complex. It sort of digitally signs it all. It needs PKI and such, so it hasn't really caught on as a security tool. As far as layer 2 security goes, well, your 802.1x and things like this still work with IPv6. And that's probably another reason why SEND really hasn't caught on. Not too many people run sort of pure IPv6 networks, and SEND, like I said, is a pain to set up and not really support in operating systems at this point. Another little thing I forgot to show you, let me just show you this quickly. Little bug here if you're playing with this yourself. When I did the netstat-g here, I did this little grep trick to only see the address I'm interested in. If you just do netstat-g, you get, of course, a long list here of different multicast addresses. It's sometimes hard to find what you're looking for. According to the man page, and let me show you that. There's some filters that we could use. So I used the -G option. And you see, I could just look for a particular interface that's I or a particular address family. It doesn't do a thing. I'm not sure exactly why. If anybody has a good answer for that. If we're doing IEN7, then an F, INET6, I still get them all. So I'm not sure what's going on here. If anybody has a solution to make those filters work in netstat, that's again Mac OS. Let me know, but doesn't work for me. That's why I just used that little grep trick. So anyway, packets will be on packettuesday.com again for you to download. There should also be links in the show note if you're watching this on YouTube. Also, the packet diagrams that I sort of have here, it's a little Excel spreadsheet. I may just put that up on packettuesday.com as well. May make it a little bit easier to follow along here. Thanks for watching again. As usual, subscribe and recommend and like and do all the things to make these watched more. That's, after all, why we're doing this. So thanks for listening and thanks for watching, and talk to you again next week.